think we should be live. Let's see. Yeah, looks like we are live. Hello. All right. Honestly, I'm just here so that I don't get fined. Yeah, it took a lot of mental juice to get down to, my office and actually do this. Yeah, it's just one of those days. I just figured, let me just start and see what happens. So that's what we're gonna do. We're just gonna do it. Just gonna get going. So this is a follow-up to our, it's another installment in our series of videos where we read through the manual for the Lingua Franca programming language. So without too much ceremony, let's just jump right in. We've done up to the time and timers chapter. Now we are, well, I don't know if you can call these chapters, but I mean, logically speaking, I think it's fair to call them chapters. Well, it's, yeah, chapters. Who cares? Anyway, we did, well, we first became aware of, what is a reactor, the fact that they have, you have inputs and outputs, you can parameterize them, and obviously, just like the more general actor model, the object or the state machine has, some state that it maintains internally. And then we talked about time and timers during the last lecture, and one of the key takeaways was that there is this lag between logical time and physical time. And depending on what you're doing, I mean, if you're doing some sort of simulation, then you definitely, I think, well, it depends again on what you're simulating. But basically, it's not impossible to have logical time be much more be more ahead of physical time. And I think I'm just now realizing that I think my screen is stuck. Let's see, screen capture, restart capture. Okay, all right. Anyway, so yes, time and timers, that was yesterday. We did a mapping of what a timer is here. We did a comparison with the set interval function in TypeScript. I mean JavaScript in general. I mean, as an example, I think this is a functionality that I think most, if not all, programming languages that are worth talking about have. Yeah, anyway. So next chapter that we'll be looking at is composing reactors. So I think we've already been introduced, at least maybe not explicitly, but we've already been introduced to this concept simply because we've seen examples of programs where you have a main reactor which then calls onto other other reactors, and it's almost like it's the glue that binds all the different reactor components of the system, whatever program is running. So I think we've already had a taste implicitly of reactor composition, which again, composition slash modularity is something you would expect for any self-respecting programming language, especially one that is an actor model based programming language. Alright, reactors can contain instances of other reactors defined in the same file or an imported file. Assume the count and scale of reactors defined in parameters and state variables are stored in files countlf and scalelf respectively, and that the test count reactor with time and timers is stored in test count. Then the following program composes one instance of each of the three. So you instantiate each one and then you connect them, and so this will be the output. So you're basically connecting inputs and outputs, and essentially you're creating a unidirectional channel between these components, right, where you have data flowing from the outputs to the inputs. I think they also have, I'm sure we are gonna come across this as we go further into the documentation, but if memory serves right, they actually have there are some specific rules around the way you can compose components, especially when it comes to instantiating multiple instances of the same components and sending, I think, multiplexing the same message across all those instances. I think they have some particular rules about how to do that. I think it does fan out, but there's no fan in, right? Fan in. Am I using the right? Yeah, I think it's fan in. I think the fan out and fan in pattern. Anyway, the point is, you cannot have, if I remember right, and again we'll probably get to this at some point in the documentation, but my understanding is that you cannot um, have multiple incoming links into the same input port, basically. Because then you have to think about, well, um, how do you order deterministically? Because remember, this is for cyber physical systems, and uh, determinism is a very big thing in in that domain. So if you have multiple links that are coming in and connecting to the same input port, like how do you determine? How do you assert that in a deterministic way that um, the order in which the messages coming through those links will be processed at runtime? Um, anyway, okay, diagrams. As soon as programs consist of more than one reactor, it becomes particularly useful to reference the diagrams that are automatically created and displayed by the Lingua Franca IDEs. The diagram for the above program is as follows. Yeah, I think I don't know how to make it show up again, but I could have sworn. Okay, there it is. Open diagram. How do I? Is this the? What is this? Layer diagram. Anyway, but yeah, this is. So if you're running this in VS Code for each lingua franca, at least from the main reactor, there is this option here at the top where you can select opening diagram, and so you'll be able to see the diagram of the state machine. In the diagram, the timer is represented by a clock-like icon here. The reactions by chevron shapes. I think it means this. And the shutdown event by diamond. This here. If there was a startup event in this program, it will appear as a circle. Creating reactor instances. A bank with several instances can be created in one such statement, as explained in the banks of reactors documentation. Okay. So you have the parameters. They are comma separated. So that can be a value, a numeric constant, a string, a time value, or some expression in the target language. Connections. Connections between ports are specified with the syntax: source, destination. Where the port references are either instance name, port name, or just port name, where the latter form is used for connections that cross hierarchical boundaries, as illustrated in the next section. On the left and right of a connection statement, you can put a comma separated list. For example, the above pair of connections can be written. Okay, so you, instead of having to do this, you can actually do it in a single statement. Okay. Excuse me. A constraint is that the total number of channels on the left match the total number on the right. In addition, some targets require the types of all the ports to be the same. Yeah, that actually sounds like a good idea. A destination port on the right can only be connected to a single source port. Yes, so this is what I was referring to a few minutes ago. However, a source port may be connected to multiple destinations. Yes. So the same source port here can be connected to multiple destinations, and that each destination may be an instance of the same reactor type, reactor object as well. Lingua Franca provides a convenient shortcut for such multicast connections, where the above two lines can be replaced by one as follows. Nice. This is a nice quality of life thing, I would imagine. The enclosing means to repeat the enclosed comma separate a list of sources, however many times is needed to provide inputs to all the sinks on the right of the connection. Yeah, this is a pretty good quality of life feature or syntax. Import statement. Alright, I mean, this looks pretty straightforward. Class name and alias can be a comma separated list of to import multiple reactors from the same file. The path, specify another LF file relative to the location of the current file. Okay. The alias portion is optional and specifies alternative class names to use in a new statement. Okay, I mean, the concept of aliases is for imports is pretty common across a whole lot of languages. Hierarchy. Reactors can be composed in arbitrarily deep hierarchies. For example, the following program combines the count and scale reactors into a container. All right. Yep. Okay. I mean, there's nothing earth-shattering here, which is good. I mean, it's just module dependencies and the deep graph that you can get from that sometimes that can lead to actually bad things. But anyway, alright, the container has a parameter named stride whose value is passed to the factor parameters of the scale reactor. Right. Oh, okay. All right. Yeah. I was like, wait, what are they talking about? All right. The line SYY establishes a connection across levels of the hierarchy. This propagates the output of a contained reactor to the output of the container. Okay, this propagates the output of a contained reactor to the output of the container. So if you think about it in terms of the DOM API, this is like an input text field having its I don't know, key press event be propagated to its parent form. I think off the top of my head, that's like a very simple example of what is being said here. A similar notation may be used to propagate the input of a container to the input of a contained reactor. Yep. Okay, connections with logical delays. Connections may include a logical delay since the after keyword. Using the after keyword as follows. So you have the source port, the destination port after time value. So what is the use case for this? The after keyword specifies that the logical time of the event delivered to the destination port will be larger than the logical time of the reaction that wrote to the source port. Okay. I get the what. I'm still not really grokking the why. I'm sure it has something to do with, the intricacies of dealing with cyber physical systems. I don't think it even has to be the cyber part necessarily has to factor into this. I think sometimes you just need some sort of buffer between as you're transitioning from a given state to another. Like if you think in terms of a scheduler like Kubernetes and how it does rollouts, or if you think of auto scaling in the cloud, with your EC2 instances, you need some sort of window of time in order to apply certain effects. I think also this relates to the concept of watermarks in stream processing. Anyway, the time value is required to be non-negative, but it can be 0. Okay, in which case the input event at the receiving will be 1 microstep later than the event that. Okay, what is 1 microstep again? Did we already go over that? Okay, no, we haven't made it to that specific concept yet, which kind of indicates that maybe this is not a great place to introduce this. Okay, so logical delays, physical connections. A subtle and rarely used variant of the arrow connection is a physical connection denoted by this. A random thought just crossed my mind. Could you rewrite the Kubernetes controller or API server in Lingua Franca? Like, what would be the pros and cons of doing that? At least from or maybe just for simulation sakes, like simulating different behaviors of the control plane or of a cluster as you know, send it a bunch of messages and you want to observe that, things are operating within, expected parameters. I think there's something there. Anyway, physical connections. A subtle and rarely used variation of the arrow connection is a physical connection denoted that, for example, squiggly arrow, I guess we'll call it. For example, A, B, and then we have this. So the output Y to the input X of B. This is rendered in by the diagram sensitizer as follows. Okay, so in such a connection, the logical time at the recipient is derived from the local physical clock. The logical time, did I say local? No, anyway, yeah, I did say local, but at the right place. Anyway, the logical time at the recipient is derived from the local physical clock rather than being equal to the logical time at the sender. Okay. So in terms of computing model here, I think stuff that we need to keep in mind, I guess, is that each reactor has an associated, logical and physical time. And I think the default scenario is that when you're sending a message via a channel between two reactors, the assumption is that the logical time between both reactors is the same. That will be the default transmission model. And then you have the physical clock component, which obviously is not guaranteed to be the same. And it sounds like this concept of physical connection is a way to account for that. Okay, the physical time will always exceed the logical time of the sender. Okay. unless fast is set to true. I mean, I can just nod my head and say, but I don't think that I fully grok this and the implications of that. The physical time will always exceed the logical time. I mean, that on its own, generally speaking, makes sense. I mean, it's the reason why we have things like vector clocks. Unless fast is true. Okay. So this type of connection incurs a non-deterministic positive logical time delay. Physical connections are useful sometimes in distributed execution. In situations where the non-deterministic logical delay is tolerable. Such connections are more efficient because timestamps need not be transmitted and messages do not need to flow through a centralized coordinator if a centralized coordinator is being used. Still not completely or entirely clear on the whole physical connection thing, but let's move on. Alright, let's do reactions. Reactions. How long do we have? Okay. I'm trying to keep today's session to 1 hour or less, which is making me question if I should. Yeah. Let's go. Let's do it. Reaction declaration. A reaction declaration has the following form. Each reaction declares its, so reactions are these. Let's see if we can find something here. Oh, they have async. What is caller? Is there some sort of oh, okay, it's not the typical async stuff. This is more of a controlled method. Anyway, reactions. Yeah, we've seen these quite a bit of time. That basically takes some sort of trigger and to run some computations. Okay, each reaction declares its trigger, uses, and effects. The triggers field can become a separated list of input ports, output ports of contained reactors. Only contained reactors, not the actual output of the reactor itself. Timers action or the special events. Startup, shutdown, and reset. There must be at least one trigger for each reaction. That makes sense. The users field, which is optional, specify input ports or output ports of contained reactors that do not trigger execution of the reaction but may be read by the reaction. Okay. That's nice. I would go as far as say maybe that should not be optional. It reminds me of the const specifier in class methods in C++, where you can add const as part of the return signature to denote the fact that the method is using fields from the object, but it does not intend on making any writes to that object. So that's nice. Yeah, I mean, I would say I wouldn't mind it if it was required. I mean, but then again, it's one of those things where on paper, you definitely want it to be something that is, well, more often than not, you probably want it to be something that's explicit, but then it can be annoying if it were enforced and required every time. I can see how it can get, annoying. All right, the effects field, which is also optional. Again, I don't know, I just keep having this feeling that I feel like it would be better off not being optional. Is a common separated lists of output ports, input ports. No, a common separated list of output ports. Okay. Input ports of contained reactors and so on. Okay, all actions. Reactions may optionally be named. The name is cosmetic. Okay, so like this here. These don't have names. Whoever wrote this definitely is not interested in giving these names. Which, it is what it is. So the naming is cosmetic and may serve as additional documentation. Note that reactions cannot be called like functions, even if they are named. All right. Good. Okay. The reaction's behavior is defined by its body, which should be given in a target programming language. Note that the reaction body may only read from actions and ports that it has declared as triggers or uses, and it may only write to actions and ports that it has declared. Oh, okay. So it's optional, as in if you're not writing, if your reaction is not doing any write operation, then it doesn't have to specify its effect. But if it is, it has to. Okay, that's good. I misunderstood earlier then. Okay, the target code generators implement a scoping mechanism such that only variables that are declared in the reaction signature are accessible in the reaction body. Nice. Nice. This eliminates a whole host of headache, assuming that it works as intended. In some targets, the reaction body may be omitted, and the body can be defined natively in the target language in an external file. Oh, okay, so you can do a reference. That's nice. Nice feature. I like it. That's actually pretty nice. Okay, reaction order. A reactor may have multiple reactions, and more than one reaction may be enabled at any given tag. Oh, okay, a tag is like an epoch of the state machine. In Lingua Franca semantics, if two or more reactions of the same reactor are simultaneously enabled, then they will be invoked sequentially in the order in which they are declared. Yeah, I was aware of this. This is the part, these semantics or these things are relevant for, if you want to be as deterministic as possible in your computation model. Anyway, more strongly, the reactions of a reactor are mutually exclusive. And are invoked in tag order primarily and declaration order secondarily. Tag order. Oh, okay. Yeah. This is a big deal. It just eliminates a whole host of headaches. Because then you can make some assumptions about how data is being processed at different steps of your program. Okay, so we have this here. You have a timer, s is equal to 0. So this program is meant to only run for 3 seconds. So we have a timer T1 that has an offset of 100 milliseconds. And then its interval is 100 milliseconds and so on. So the point of this is that some of these are going to overlap in how they are executed. So this is going to, so the offset, so this will be 100 millisecond after startup. And that's when you'll have the first one. And by the time the second tick for this timer comes around, this one will also be triggered basically at the same time. And then the second run of this is going to coincide with the first round of this. Okay, so every 100 milliseconds, this increments the state variable s by 1, every blah, when. Sorry, I'm not reading all of that. I think it's basically saying what we just went through. When these reactions align, they are invoked in declaration order, and as a result, the printed value of s is always 0. There's something to be said about, so that may not be the behavior that you want, right? But at least there's something to be said about the fact that this is deterministic. Like when multiple reactions happen to be triggered, in the same tag or slash epoch, you know exactly the order in which they're supposed to execute. And, based on that, understand some behaviors, both wanted or unwanted, of your system. Overriding outputs. Just as the reactions of the alignment reactor override the state variable s, logically simultaneous reactions logical simultaneous reactions can override outputs. Consider the following example. So this is triggered by the timer, and then offset of 100, and then every 100 milliseconds. So here we are updating a state, but we also are sending something to the output. So on the second run of this timer, the first run of T2 will also be triggered. So we'll first do +1, which will be 2 at that point, and we would have sent so first time around we will have sent 1 to the output. Then this time around it will be 2, but it will immediately enter this reaction right after, and that s becomes 0 again, and the output also gets overridden to be 0 again. And then the timer one's third run goes into effect, and you basically start over, and so that's how you end up with 1 0 1 0, so on. Yeah. Okay, reacting to outputs of contained reactors. A reaction may be triggered by I'm gonna just assume that this was meant to be by an input to the reactor, but also by an output of a contained reactor. That makes sense? Yep. Nothing overshadowing here. This instantiates the above overriding blah blah blah. Okay, triggered contain reactors. A reactor can set the input of a contained reactor, thereby triggering its reactions, as illustrated in the following example. So here we have inside, and this will be the input channel / port. And so you instantiate, and then on startup you basically send something into that. Okay. Ooh. Okay. Yeah. Okay. I mean, this makes sense. All right. Startup, shutdown, and reset actions. Reactions may be triggered by the special events startup, shutdown, and reset. A reaction to startup is triggered at the very first tag when the program begins. And if within a mode of a model reactor, we'll get to that at some point, when the mode is first entered, this reaction will be logically simultaneous with reactions to timers that have zero offset. As usual, for logically simultaneous reactions declared within the same reactor, the order in which they are invoked will be governed by the order in which they are declared. A reaction to shutdown is invoked at program termination. Then the reset event is invoked if the reaction of reactor is within a mode of model reactor, and the mode is entered via reset. All right. I think we'll stop here. We only did 2 chapters. Not terrible for somebody who was trying to make a decision between going to lie in bed and showing his face on camera while reading some technical manual or some programming language manual. Not too shabby. Yes, okay. Sorry, I was starting to go down some what are they called? Anyway. All right. I'm gonna call it. If this was useful in any way, please do like and subscribe, and I'll see you around for more Lingua Franca tomorrow. probably, maybe. We'll see. All right.